Okay, good morning. Let's start again. Today we are going to finish chapter 3. Start chapter 4, Grand Canonical Ensemble. And the last topic in this chapter is negative temperatures. Of course, we are talking about magnetic systems. Here, I will consider again the simplest case of J equals 1/2. You can consider a spin 1/2 particle so that it has two directions in a magnetic field, up and down. So two orientations with energies minus mu BH or plus mu BH. If they are in the same direction, remember minus mu dot H. If they are in the same direction, it's minus mu H. If they are in opposite directions, then it is plus mu H, higher lying state. The other one is the ground state. Let's see the partition function once more. Very simple. Single partition function, single particle partition function is e to the beta e plus e to the minus beta e to the power n. If they are distinguishable, if they are sitting at lattice points, spatially we know where they are, so they are distinguishable. You can write the partition function as 2 cosine hyperbolic beta e to the power n. And of course, this is minus e, that is plus e. E is nothing but mu b h. So, entropy, after you are able to write the partition function, you can get all the thermodynamics from it. And entropy, or let's start with the Helmholtz free energy, A, is minus kBT ln to n beta. Since E's are constant, beta is 1 over kBT, so your partition function depends on beta, temperature only, isn't it? So that is Helmholtz free energy and kBT minus, and then 2 cosine hyperbolic E over kBT in explicit form. Okay? Can you see? So you have to change your place. If you know Helmholtz free energy, you can get entropy as minus del A del T, keeping H constant. I have done this thermodynamics before, so you can easily follow the same recipe. That is NKB ln 2 cos I'm trying to write everything in terms of temperature. That's the derivative. So we know everything. Let's complete the thermodynamical quantities of this very simple system. Energy, by definition, A plus Ts, and we know both A and S, so it is straightforward to write minus NE, tangent hyperbolic, E over kVt. See, we have all the quantities as a function of temperature. Magnetization. That's also a very simple derivative. Comes out to be N mu B, tangent hyperbolic. Everything is coming up nicely, analytically. And of course, you can note that it is nothing but minus m times h, as you expect. And finally, the response function, heat capacity, du dt, nkb, derivatives, simple derivatives. Okay, the whole thermodynamics is coming up very nicely, very simply. We have all the important functions explicit as functions of temperature. So let's draw them as a function of temperature. And I think you should know this recipe, getting the partition function, going to Helmholtz free energy, and from Helmholtz free energy get all the thermodynamics. Quite a simple recipe to follow. But now, of course, physics functions have physics in them, so we have to discover that. Can see everything by plotting the temperature dependence of different quantities. Here is the entropy in units of nkb. There is a limit, and here it is. As a function of temperature, in that unit of energy in our case is epsilon or E kVt over mu h, if you like. It properly goes to zero when temperature goes to zero in accordance with third law of thermodynamics, and it goes to a limit ln2 for higher temperatures. Because you have two states, it was proportional to logarithm of number of available states. So it properly, two particles have 2 to the n equal likely microstates. So n ln2 is the limit. Okay, everything is okay. Let's look at the energy. Energy as a function of kBt over E. This is U in units of N times E. Energy is negative, so it goes like something like this. -1. What is it for -1 and why it's going to 0? Here comes the physics, of course. When temperature is very large, disorder sets in. The spins are randomly oriented at high temperatures. So if half is in one direction, half is the other direction, the energy should be 0, positive and negative. And this one, all of them are aligned with the magnetic field at low temperatures. Remember, temperature kills the magnetism. So it's complete saturation, isn't it? They are all in the same direction, so you have the negative value, minus N times E. Well, magnetization is also reflecting the same behavior. Magnetization is as a function of temperature, kBt over E, m over N times mu. At low temperatures, everything is magnetized in the same direction, so it must start from 1. And as temperature is becoming larger and larger, magnetization will be killed. It will go to 0. So it's something like this. If you plot this as a function of magnetic field, we are going to see a similar effect. It will go to a full magnetization as you increase the magnetic field. Magnetic field creates magnetism, temperature kills it. So, everything is coming up quite nicely. Now, heat capacity, C, as in units of nkB, kBt over E. Well, it has a nice behavior. First, it goes to 0 as temperature goes to 0. That's in accordance with third law of thermodynamics. Perfect, okay. Vanishes as T goes to infinity because energy is going to be a constant. That's also okay, isn't it? There's a maximum at temperatures corresponding to E over kB. It displays a maximum at that temperature. This is known as Schottky anomaly. You always have this type of heat capacity if the system has an excitation gap. Okay? There's an excitation gap. Let's call it delta. This is the energy difference between two allowed states. isn't it? You have to excite the if it is an electron from ground state to the excited state. In terms of this excitation gap, you can write the C as NKB. Why don't you do this? Delta over KBT squared e to the delta over KBT 1 plus e to the delta over KBT minus 2. Delta is of the order of mu times h, isn't it? The difference between the two states is of the order of mu h. So whenever you see a maximum in heat capacity, you should get excited. Do you know other systems where there are an excitation gap? The most famous? Is it superconductivity, for example? Yeah? Now, there is one more exciting, interesting aspect of this problem. Negative temperatures, as I have written at the beginning. Now, there's, well, in these cases that I plotted, I always considered the case of positive temperatures, isn't it? And that's what we are used to. Now, one thing that is important in this problem is that energy is bounded above, isn't it? Is bounded. If that is the case for any physical system, then there's this interesting phenomenon. You cannot exclude the possibility of T negative in this case. Let's check that. First, recalling what the energy is. Tangent hyperbolic E over KBT. Now, if U is negative, then T is positive. That's what we have seen. But if U is positive, then there is a possibility that T is negative. Simply because tangent hyperbolic x as a function of x is something like this, isn't it? So if x is negative, the function is negative. Tangent, inverse tangent hyperbolic, that will give us the temperature, minus x is minus tangent hyperbolic inverse x. That gives us the possibility of negative temperatures. Now, let's write the temperature explicitly. Inverting the function, tangent hyperbolic inverse minus u and e, or minus tangent hyperbolic inverse U over N E. Now, that's the explicit possibility for negative temperatures. Another form you can use in writing this is that tangent hyperbolic inverse is 1/2 logarithm 1 plus x 1 minus x if x squared is between 0 and 1. So one more important thing, using this, 1 over t becomes kb 2 epsilon ln n epsilon minus u n epsilon plus u. Now, of course, in this problem, negative energy is what you expect when you magnetize a system. When do you get positive energies? How do you get positive energies? Experimentally, what should you do to put the system into a positive energy state? Can you suggest anything? You apply a magnetic field, you magnetize the system, spins are in the same direction, lower the temperature if you like. Now, what should you do to catch the system in a positive energy state? A state in which spins and magnetic field will be in opposite directions, aren't they? In that case, energy will be positive. How can you do that? I thought you have done this problem in undergraduate course. The experiment is done in lithium fluoride in 1951. I will give you the reference so you can check the experiment. It is an interesting one. Experiment is done by Purcell and Pound. PHYS 81. Using lithium fluoride, and there's a good reason for this. Lithium fluoride has spin-spin relaxation time T1 smaller than 10 to the minus 5 seconds, and spin lattice relaxation time is about 5 minutes. So The trick is all of a sudden reversing the magnetic field. You magnetize the system, reverse the magnetic field, and that state must persist a couple of minutes so that you can do the experiment. And with this relaxation times, you can manage that. The time it takes to follow the reversal of magnetic field is long enough so you can catch the system in the opposite spin state, positive energy state. Okay? But it is a curious state. Negative temperatures, well, you have to really look up the problem again, read your book, is a hotter state. It's positive energy, isn't it? It's a hotter state. Very curious physical phenomenon and experimentally observed. It's a nice experiment. Okay? So this teaches us something. It tells us that simple looking physics may have surprises for you. Huh? Yeah?
I don't understand that. If we increase the temperature, the magnetization kills. Temperature kills the magnetization.
Yes.
So, if we have the opposite spin here, and if it is the hot state, then magnetization shouldn't be there, right? But what's the meaning of hot state?
The magnetization is there, but it is in the wrong direction.
Okay.
Since you apply the magnetic field, you magnetize the system.
Okay.
You align the spins in the direction of magnetic
What's
field by... Huh?
And temperature?
Temperature is positive.
Okay.
Now all of a sudden you turn the magnetic field for a couple of minutes. It's not an equilibrium state. For a couple of minutes, you keep the system in a strange state. Magnetic field is in one direction, spins are in the other direction. Of course, eventually spins will follow the magnetic field depending on these relaxation times, but it takes 5 minutes. Spin lattice relaxation time is 5 minutes. If they are free, okay, they may follow easily, but in a crystal, the spin lattice relaxation time being so long, it takes some time for them to follow the magnetic field. So it is not an equilibrium state. It is a funny state you can catch the system in for a short time. Then, of course, spins will follow the magnetic field. You are going to end up with the same equilibrium state. Okay? Good. I think your book is quite good in this. Follow it. Do the calculations yourself and convince yourself that that is a possibility. Okay? So I underline again, you should look at the simplest problems from the physics point of view. What is the physics behind these expressions? Okay? Well, that's the end of chapter 3. I'm going to go to chapter 4, which is grand canonical ensemble. And as usual, at the end of the chapter, I give you the related homework to that chapter, okay? Now, I am in some sense reviewing what you should have done in undergraduate statistical thermodynamics course, of course, with a graduate touch. Now, I will do the same with the grand canonical ensemble. With this an incoming chapter on quantum systems, quantum statistical mechanics, we are going to finish one part of the course. That has to follow by a midterm. Midterm number 1 will include the basics of statistical mechanics and some thermodynamics. So I think as a class we should discuss a possible date. At the end of the chapter 5, I will give the midterm number 1. Okay? Get ready for it. Now, let me remind you what I have done for the grand canonical ensemble. Remember, this is a collection of systems for which we have energy and particle exchange. So the systems making up the grand canonical ensemble are interacting with a heat and particle reservoir and exchanging heat, that means energy, and particles with the reservoir. Okay? So this is in some sense the most general case, isn't it? Your system is interacting with a heat and particle reservoir. In this case, I got for you the probabilities of finding the system in a specific energy state with a specific number of particles. Let's recall what we have done up to now. And now we are going to apply that knowledge to specific systems. Okay, let's go to chapter 4. The probability I'm talking about was found to be given as a Gibbs factor, remember? Exponential minus alpha n r minus beta es normalizing factor, which is also known as grand canonical partition function. Okay. Where alpha was defined to be minus mu over kBt. When there is a particle exchange, of course, the driving force is the chemical potential difference, gradient in chemical potential. Particles will flow from high mu to low mu regions, towards low mu regions, isn't it? That means your system and the particle reservoir. And beta is the usual 1 over kBt. Sum is over all states, NR and ES states accessible to the system. I showed the sum as over R and S, number of particles and energy states. In canonical ensemble, we had only a sum over states available to the system. Not the number of particles, but here number of particles is also fluctuating. So that's the important difference. Averages can be written in terms of the probability, the quantity times the probability, sum over all available states gives you the average. Here it is, sum over all possible states, quantity, whose average we are taking, times the probability. That's average number of particles in your system. Of course, this can be written in terms of the partition function itself, because to bring down an NR from exponential, you just take a derivative with respect to alpha. Negative of derivative with respect to alpha brings down an NR, isn't it? So, can write this as minus derivative with respect to alpha, 1 over the function. That means you have to take derivative of the logarithm of the partition function, ln rs exponential Well, similarly, you can write the average energy as, well, how can you bring down an energy instead of nr? By taking derivative with respect to beta, minus the derivative with respect to beta, minus del over del beta, ln this sum is our grand canonical partition function. Let's write that explicitly as the partition function. Grand canonical partition function. How should I write this? Let me write this like that. Is it curly Q? It's better to write it this way, probably. Curly Q. This is sum over all possible states and number of particles minus alpha and r minus beta ds. That's the partition function. Grand canonical partition function. And that's what we have done up to now. In my extended first chapter treatment, I have obtained this, remember, by counting the states available to the heat and particle reservoir. Remember this in the first chapter? Okay. Now, we have to have a similar recipe for the grand canonical ensemble to get the thermodynamics. How are we going to get the whole thermodynamics? By using the partition function. It is, again, straightforward. Let's do this by defining a new function, Q potential. Okay? In some books, this is omega, lambda free energy, but in your book, Patria, it is the Q potential. So whose derivatives will give us the thermodynamics. Q potential is defined as follows. Q, well, remember in the averages, what did we have? Derivatives of what? Logarithm of the partition function, isn't it? So that's the Q potential defined as ln of the partition function. We were taking derivatives of this function to get the averages. So it is quite practical to define it as the Q potential, whose derivatives will give us the average values. Huh? You can treat this as a function of alpha, which is related to chemical potential, function of alpha, beta, temperature, and the available energy states. ES, energy ES. So let's try to go from here to the thermodynamics. Very first thing you can do is to be able to write dq. You can do this as n bar d alpha. If you take derivative of q with respect to alpha minus the derivative was giving this average value, wasn't it? Similarly, minus e bar d beta, derivative of this with respect to beta negative was giving the average energy. And one more term, beta capital N RS average of N DES. Well, that average is average N, isn't it? You have to think about this term. If you take derivative of this with respect to E, you bring down a beta. Well, it looks like a mathematical game, but it's not really. This is N bar, N capital, so it doesn't take too long to come to the following. We should discover this path to thermodynamics. You can rewrite this as dq plus alpha n bar plus beta e bar as beta alpha over beta d n bar average, in other words, d bar minus 1 over n capital NRS DS. That's the expression. And first law gives you dE or du as d bar q minus d bar w, the work done, plus mu d n bar. Huh? That's the first law of thermodynamics. Or you can write this as the heat intake as d plus d omega minus mu d n bar. So if you look at the expression, you can identify the work, infinitesimal work done as minus 1 over n rs n rs des. And mu, remember, the chemical potential was related to alpha as alpha over beta. So this quantity then, the Q plus alpha n bar, beta E bar is beta D bar Q. Beta is 1 over kBt. Or, here comes the thermodynamics. Q plus alpha n bar plus beta E bar is nothing but entropy in units of kb, or Q is nothing but Ts plus mu n minus average energy over kBt. Now, what is mu times n? Mu, chemical potential, and number of particles. Gibbs free energy, isn't it? Gibbs free energy, or mu is Gibbs free energy per particle, G over n. So, mu n bar can be written as G, Gibbs free energy, which is nothing but E bar minus Ts plus PV. So this is telling us then that the Q potential is nothing but PV over kBt. This is the link between thermodynamics and ground canonical ensemble. Now I will introduce one more parameter, which is known as fugacity. The parameter is called Z and defined to be minus e to the minus alpha. So it is putting what alpha is, mu over kBt. I will tell you a little bit about the physical meaning of this quantity. This is just a definition. Okay, very simple definition of fugacity. So in terms of this partition function, And the Q potential can be written as ln, the sum, the partition function takes a simple form, simple looking form, z to the nr, q and r vt. This is the canonical partition function, q, straightforward q. Okay? So it is a sum over particle number, z to the n, q to n. Canonical partition function gives us the grand canonical partition function. So you have to do a little bit more after you do the canonical calculation. Okay. A more complicated ensemble in that sense. And of course, remember, Q0 is 1. If you like, you can simply write the grand canonical partition function as, well, Q now it is to be written in terms of independent parameters Z, the fugacity, volume, and temperature, as instead of an R, we can generalize it, write N, okay? Finding the system with particle number N. So it is N from 0 to infinity, Z to the N, Q, N, Vt. This Q, I repeat, is the canonical partition function. That is grand canonical partition function, like a curly Q. Okay. So Q potential then is nothing but ln Q. Now you have to do this calculation with fixed n in the canonical partition function case, and do that sum over all particle numbers. Now, of course, this looks like an added complication, and easier to do the things in canonical ensemble, but you will see that grand canonical ensemble will be easier if you are dealing with quantum statistics and if there are interactions between particles. Okay? So that's where you get the most out of grand canonical ensemble, as we are going to do for the quantum systems. Our next subject of study, of course, we are going to concentrate on fermions and bosons, quantum particles. There we are going to use grand canonical ensemble. These are the basic things that you have to remember, the definitions and the full recipe. Let's get the full recipe now with these two things, grand canonical partition function and the Q potential. How are we going to write the whole thermodynamics. Let's start from pressure. Of course, when you take Z, V, and T as your independent parameters, then you don't have to relate, well, at the end you can relate Z to chemical potential, but you are not going to take derivatives with respect to chemical potential here. Z is the independent variable. The pressure is, well, we have found that, remember, was kBT V over V times Q, ZVT. So it is related to the partition function grand canonical partition function as kBT over V times ln Q. So if you know grand canonical partition function, you know the pressure. Let's get the other quantities to complete the recipe for thermodynamics in grand canonical ensemble. I forgot to look at my watch. Let's give a break. 10 minutes. Okay, I will continue with this program.